Okay, and we've got one more item for you when you get a chance. We'd like it to stir up your cryo tanks. In addition, I have a shaft and trunnion for a look at the Comet Bennett if you need it.
Stand by. Okay, Houston, we've had a problem here.
This is Houston. Say again, please.
Houston, we've had a problem. We've had a main B bus undervolt.
Roger, main B undervolt. Stand by, 13. We're looking at it.
Ignition sequence start. 6, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Okay, we got a roll program. Okay, we got a roll program. Okay, we got a roll program.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on a proper heading. Plus 30 seconds.
Roll complete and a pitches program. Roll complete and a pitches program. Roll complete and a pitches program.
Man on the way to the moon. What did it feel like? It felt like a train on a bad railroad track and shaking in every direction. And it was loud, really loud.
The noise level of a rocket engine is up into the 140, 150 decibel range. In other words, enormously loud. How would it be possible to hear astronauts' voices against the background of a running rocket engine?
Picking up some dust. 30 feet, 2.5 down. Straight shadow. 4 forward, drifting to the right a little. Contact light. Okay, engine stop. 6, 5, 4, 3, 2, 1, 0. We have ignition. What a liftoff. And liftoff. Roger, ignition. Smooth. Pitch over. Pitch over. 10 seconds. Roger. Hey, baby. It's good. Proceeded. 3, 2, 1. Ignition. Right away, Houston. Vector good. Ag thought. Pitch over. Roger, you have good thrust. Okay. your number. Okay, coming through 1,500 feet, and H-dot looks good.
Six, 5, 4, 3, 2, 1, 0. All engine running. Liftoff. We have a liftoff. 32 minutes past the hour. Liftoff on Apollo 11. Tower cleared.
Okay, we got a roll program.
Neil Armstrong reporting the roll and pitch program, which puts Apollo 11 on proper heading. Plus 30 seconds.
Roll complete and pitches program.
What did it feel like? It felt like a train on a bad railroad track and shaking in every direction. And it was loud, really loud.
Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program. Okay, we got a roll program. Roll complete and pitches program.
You sometimes seem uncomfortable with your celebrity, that you'd rather not have all of this attention.
No, I just don't deserve it.
If you were to rocket out into space 20 miles and then look back, the receding Earth would look like this. For the story of the hazards of Earth's radiation belts, danger that lie beyond our atmosphere, stay tuned to Science in Action. American Trust Company, for the 10th year on television, proudly brings you Science in Action, produced by the West's oldest scientific institution, the California Academy of Sciences.
The Earth is ringed by two zones of high-energy particles. These areas are now called the Van Allen radiation belts in honor of the physicist whose work led to their discovery. The existence of the Earth's radiation belts presents a very serious hazard to future space travel. What is the intensity of this radiation? What does it consist of? How much shielding will the first space travelers need in order to penetrate these deadly areas of radiation safely? As a result of a unique experiment, some of these questions have been answered. And to tell us this remarkable story, we've invited the two scientists who conceived and carried out this project. Our first guest is the leader of the Nuclear Effects Group for the University of California's Lawrence Radiation Laboratory, located at Livermore, California. I'd like to have you meet Dr. R. Stephen White. Welcome to Science in Action, Steve. How are you?
Thank you, Earl. It's a pleasure to be here.
I would like to know what it was that gave Dr. Van Allen the first clue to the existence of these radiation belts.
The first clue, Earl, was furnished by a raccoon.
Well, I know raccoons, but raccoon, I'm not quite sure.
Well, it's quite an appropriate name, Earl. A raccoon is made up of a balloon and a rocket hung from that balloon, and they were launched from the deck of a ship. Dr. Van Allen, back in 1953, was doing some cosmic ray research in the vicinity of the northern auroral zones. You know where the northern lights are?
Yes.
And during some routine experiments, about 30 miles up, he ran into an area of radiation far stronger than anyone had expected.
Well, at the time, did he have any idea what the cause of this radiation was?
No, it puzzled everyone. Further experiments were needed at higher altitudes than the raccoons were capable of reaching. The chance came in 1958 when Explorer 1 went into orbit, and it carried cosmic ray detectors and a transmitter designed by Dr. Van Allen's group.
Over here in this next section, we have sketched the orbit of Explorer 1, and I notice that down here it's very close to the Earth, whereas up here it's quite far apart. That is quite a distance from the Earth. Perhaps you could put that mileage indicator 200 miles at that point, and then I will put this one up here, which indicates 1,500 miles from the Earth at this section.
Well, this is what brought the first surprise, Earl. At the 200-mile level, the counting rate was just as expected. But as the satellite went to higher altitudes, above 600 miles, the radiation increased and then dropped to zero.
Well, that would seem to indicate that perhaps there was no radiation up here, and yet everything I read has said that the further you go out, the more radiation you pick up.
That's right, Earl. That's just what happens. And this left Dr. Van Allen with only one explanation. He quite naturally assumed that his detectors weren't working properly. The chance came to check this experiment when Explorer 3 went into orbit with equipment similar to that carried by Explorer 1.
And what kind of results did he have that time?
Just about the same thing. At the lower altitudes, the counting rate was low. But at the higher altitudes, the counting rate went up and then mysteriously dropped to zero.
Well, then either the equipment wasn't working properly, or perhaps there just wasn't any radiation up here.
Well, as it turned out, Earl, neither was the case. And I'll show you on this next demonstration here exactly what happened. This is a Geiger counter designed on the same principle as that used by Dr. Van Allen in the Explorer flight. As we go on up to 2,000 miles, we have here with us Joe Hilson from the effects group at Livermore, who will put in the cobalt-60 source, which will serve as a source of radiation for the experiment.
That goes right at the top of the...
That's right in the middle of the belt. You'll notice the counter went up here as he stuck that source in.
Yes.
Now, I will turn on the sound here, and we'll imagine that the Explorer is mounted in, that the counter is mounted in the Explorer satellite, and you can hear the counts here, you can hear the sound, and you can also notice the reading on the meter. Now, I'll start the takeoff here, and you can see the radiation mount as the satellite goes to higher altitudes. And you'll notice it gets pretty high here. It goes up just as we would expect as it gets closer to the radiation source.
This is the same thing that happened in Dr. Van Allen's experiment.
Exactly. And now we'll jump above 600 miles, and we'll see what happens when we get closer to the source of radiation.
Uh-oh, there it goes back down to zero again.
Yes. The explanation for this is that the satellite had gotten into an area of radiation so strong that the counters were completely jammed. Now we'll return the satellite back down to the lower level, away from the radiation.
In other words, it went back to zero and then came back up again.
That's right, and you can see it's still very high there, Earl. Now we'll go on down to the lower altitude yet. And you can see the counter is now working normally, just as if nothing is wrong.
Well, then it was a question of equipment which was designed to be very, very sensitive, but couldn't take the amount of radiation which was in this area way up above the surface of the Earth.
Exactly, Earl. Dr. Van Allen had run into an area of radiation far stronger than he had expected, and his counters just weren't designed to detect such strong radiation. The confirmation of this discovery came with Explorer 4. The lunar moon rocket, Pioneer 3,
yes,
went out 65,000 miles and not only confirmed these discoveries, but also found a second radiation belt farther out.
Well, to find out the relationship of these two radiation belts, we have set up over here in this next section an exploded arrangement of what this might look like, of course, with the Earth right here in the center.
Well, you can see here there are two distinct belts, Earl. Both surround the Earth like huge donuts, with holes at the top and the bottom. Now, the inner radiation belt has its maximum intensity at about 2,000 miles out, while the outer radiation belt has its maximum intensity at about 10,000 miles.
Now, when you talk about the intensity of radiation, what is this going to mean to the first person who takes off from the Earth as a space traveler?
Well, Dr. Van Allen estimated that the intensity in the inner belt was about 10 roentgens per hour, and the intensity in the outer belt was several times that. The human body should not be exposed to more than about 1 Roentgen per month over an extended period of time.
Well, obviously, then, some kind of protective material is going to be required to enable this person to make the flight.
Yes, the first traveler will probably go into orbit at something like 400 miles from the surface of the Earth.
This would be the radiation belt right here.
That's the lower radiation belt, and there are about 200 miles separating the radiation belt and the orbit of the space traveler. But to go farther out, for example, if he wanted to go to the moon, there are two possibilities. Now let me go back to this diagram to show one possibility. That would be for the rocket to go out through one of the holes in the donut, but to come back in through one of these holes is a different problem, and it would be very difficult to do without passing through one or both of the radiation zones.
Well then, if, as you say, he's going to have to go through this radiation belt to get back to the surface of the Earth, or perhaps even to go out, then he's going to have very, very good protective materials.
That's right, Earl. In order to determine the amount of shielding required, it was necessary to obtain more information about the nature and the energy of the particles that cause the radiation.
We are headed 3,600 miles above Earth, 15 times higher from the planet than the International Space Station. As we get further away from Earth, we'll pass through the Van Allen belts, an area of dangerous radiation. Radiation like this could harm the guidance systems, onboard computers, or other electronics on Orion. Naturally, we have to pass through this danger zone twice, once up and once back. Sensors aboard will record radiation levels for scientists to study. We must solve these challenges before we send people through this region of space. We must solve these challenges before we send people through this region of space. We must solve these challenges before we send people through this region of space.
Some of these reach the outer belt and become trapped. Others strike the atmosphere of the Earth near the north and south magnetic poles and set off the electrical disturbances which we commonly call the aurora or the northern lights.
Well, all of this information to me most certainly points up the penetrating power of these and the necessity of good shielding if we're ever to have space travel.
Well, Earl, we found the radiation intensity due to protons at 800 miles is about 1 Roentgen per hour. Combining Dr. Van Allen's data with ours, we found that the radiation intensity, where it is most intense, that is in the middle of the inner radiation belt about 2,000 miles out, the radiation intensity is about 100 Roentgens per hour.
100 Roentgens per hour, and earlier I think we said that 1 per month is about all that a person should have normally. So what do we do about this?
Well, the inner radiation belt is certainly a potential hazard, Earl, but shielding may be the answer. Any space vehicle will stop the electrons and the low energy protons, but it will take 1 inch of lead to stop 90% of the protons, and it would take 6 inches to stop 99% of the protons.
Here to reveal a plan for a trip around the moon is the chief of the guided missile development at the United States Army's Redstone Arsenal, Dr. Werner von Braun.
A voyage around the moon must be made in 2 phases. A rocket ship taking off from the Earth's surface will use almost all the fuel it can carry just to attain a speed great enough to balance the pull of gravity. Unpowered, it will then keep circling the Earth in an orbit outside of the atmosphere. This is the first phase. However, if we can refuel the ship in this orbit with fuel brought up by cargo rocket ships, it can set out on the second phase, the trip around the moon and back. To facilitate this refueling operation, we will establish an advanced base in the orbit, 1,000 miles above the Earth. This advanced base, or space station, will be headquarters for the final ascent to the moon.
3 feet per second, 30, 2 feet per second, looking great, 20 feet, 10, 3 feet per second, contact now. Stop. Auto. We're on the surface. Okay, we made it.